Hello and welcome everyone. Welcome back to the video lectures, where today we are going to go into regression and classification. In a previous lecture we alluded to the fact that given enough data, at some point it doesn't make sense for us to extract manual rules anymore to get certain patterns out of data, and we need the help of algorithms. Now this week this is exactly what we'll be doing. I will be looking at some algorithms. This particular lecture focuses on some of the theory, and then the next one will delve into a bit more of applied practices of these algorithms. Now, typically the goals of a sort of data mining workflow can be broken down into three components. The first one of which is handling data, so that is, after it is collected, investigating if there are certain errors or anomalies in this data, describing it using certain statistics. Once we understand our data, we can start sanitizing it so that it becomes a bit more handleable for our algorithms. And here we already run into something that is quite a given in data mining research, which is that this part right over here is 80% of the work. And this part right here, which is most of the interesting stuff, is 20% of the work. However, once you start describing this in research, these things flip. So this will be 80% of the work to describe, whereas this will be 20%. And you can expect the same if you are going to write a thesis on these topics. So we find these patterns through algorithms, and specifically the variety of algorithms that are all applied within the data mining domain. Things that you might frequently see are words like classification, clustering, regression, rule mining, outlier detection, summarization, and all this kind of good stuff. So today we will focus on classification and regression. And contrary to some of these algorithms that I just named, these are predictive algorithms, which means that given some input data, we always try to predict a particular target using often machine learning algorithms. And these are generally boiled down into regression and classification. That is, the prediction tasks are different. And in this lecture, we'll have a look at how these are different, both from a practical standpoint, but also how under the hood they optimize different things. All right, so what generally makes this prediction possible? As I alluded to, we need some data, which is specifically, we'll talk about features. Now, a given feature we denote as X, and then we have a target variable which we denote as Y. This could be a whole range of things. This could be products that are labeled as particular categories, and say that we have images of, for example, shoes and umbrellas, and then we want to distinguish automatically if something is a shoe or a umbrella, so that we can do kind of automatic labeling. It could be pictures of people. And we might want to do something slightly inherently silly, such as predicting their age, given what they look like. And we might find certain features there, such as skin complexity or wrinkles, that might give some information about why. We could have particular documents that we want to classify as being spam, for example, or not spam. We could have an audio stream where we want to cut up the continuous audio stream in different words so that we might transcribe them. So really, X could be whatever. It's just numbers. And as long as they are numbers, we can use them for prediction. Obviously, these numbers might have different ranges and so on, and the algorithms will treat them a bit differently given the type of input data. There are certain algorithms that can, for example, only handle binary data, which is only zeros and ones. But typically, if you use a library, this is kind of handled for you anyway, so you don't have to worry about this that much. What you do have to worry about is Y, which could either be numerical or categorical. Now, numerical could be, for example, age. If we want to predict age, that could be any number between 0 and scaling up for the future, 150, right? Whereas with categorical, could be shoes or umbrellas, right? These would be mapped to a particular number as well. So shoes would be 0, for example, and our umbrellas could be 1. And as you can see, these are what we call enumerable or a limited set of things that we can investigate. There are only two options here. Now age is obviously limited, also between 0 and 150, but you can see that we already have many more target values than we would for this classification problem right here. Now it's also good to note that we distinguished two types of learning algorithms that can extract these predictions. And we have supervised and unsupervised learning. Supervised learning is where we have many instances. We give our algorithm these instances, and with all these instances comes a label that tells the algorithm this is this particular class or this particular value. And then from that, the algorithm can extract some type of representation of a particular class. So if you would use image features, for example, such as in computer vision, there would be these kind of local, what we call bags of features. So a shoe is represented as multiple kind of patches. And then the algorithm can spot that, for example, there's a kind of long object here and this kind of edge over there. And it can spot that there's a round piece over here and kind of a heel looking thing over there. And through these kind of features, it can distinguish eventually that these shapes belong to either an umbrella or a shoe. And it knows this because of why, right? We explicitly tell it, the algorithm, this is a shoe. These are the features for the shoe. Please figure out why this is different than the umbrella. Whereas with unsupervised learning, we would toss all these images at an algorithm and tell it there are different things in this set. And we could tell it that there are two, for example. There's two different things in the set. But we're not going to explicitly tell them this instance is this label, this instance is that label, right? That's for the algorithm to figure out. So this is unsupervised. And unsupervised is handy when we simply don't have the labels. Somehow these labels need to, they need to be supplied with the data set or annotated, for example, by people that go through these sets and label everything. Now, if these labels are missing, we can't use them. So if we still need some information from this set, we can only use unsupervised learning. So this lecture, we're going into supervised learning specifically. Many of the algorithms that we will discuss are supervised. Once we go a bit further into the course, we will, for example, discuss clustering, which is a good unsupervised learning method. Now, at the heart of every prediction problem lies some relation between the features or the data and the label. We, as humans, often know that particular data does have some information and we can distinguish, for example, a shoe and an umbrella. So we know that there are distinguishable features, right? We just have to figure out a way to provide this to an algorithm so that the algorithm can also figure it out. But if there's no relation to the data and the target, we'll never find a good prediction, right? Because we wouldn't be able to figure it out ourselves either. So often you can't expect just magic to happen. There always needs to be something that can be traced back to the labels that we give. So a good way to test this, which is usually standard in any statistics course, you'll be explained what correlation is. I'll go through it anyway. So correlation is a metric to measure, in a nutshell, how much similarity is between two features, two numerical features. And that typically means that if x goes up in value, so does y. Right? So if you would plot this as a line, it would be perfectly diagonal, then we have a 100% correlation between these two features, or a feature and a label. So the way that we calculate correlation is that given a particular vector or the values for these two features, or a feature and a label, let's suppose x is 2 and 4, and y is 1 and 3, and we iterate through these. So that's this summation mark right here, and I is either the 0th position or the 1st position, and this right over here would be the mean of that particular value. So for this one, that's 3. And for this one, that's 2. So essentially, we do 2 minus 3 times 1 minus 2, and then plus 4 minus 3 times 3 minus 2. So this would be solving the upper part right here. And then you can kind of do the same for the lower part right here. Just kind of calculate this yourself. And if you go through that with the values that I supplied, there should be a 100% correlation. Now, 2 more interesting things to note here is that the calculation that we just did for the top part is actually calculating the covariance. And in the Pearson correlation coefficient, the covariance is normalized, which is the lower part. And these are the standard deviations for both of the variables, of which we take the product, and that normalizes covariance so that the magnitude of the values doesn't impact the covariance interpretation. Now we'll go into some examples of this using the very classic iris dataset, which is a dataset containing these nice flowers that any course dealing with any type of machine learning is going to throw at you. And we have these 3 nice flowers over here. There's the versicolor, the setosa, and the virginica. These flowers have, as you can see, sepals and petals. Now the petals are the upper parts right here. You can see here from the top. And the sepals are the colored ones over here. Okay, now we'll have a width and a length, and through this we'd like to say which of the species of this particular flower this is. So we can plot essentially what the correlation is between these features, and then we can say something about any of these 2 features. For example, if we run the sepal length and the sepal width, you can see that it's fairly scattered, right? So if we would want to draw a line here, you know, it's probably going to go either that way or this way right here. But we won't know for sure unless we calculate the correlation coefficient, which if we run this data set is going to give us a negative correlation of 0.421, meaning that if one increases, the other decreases, or the other way around. So for this particular set, it will probably look like this. So essentially, the larger the longer the sepal, the smaller or the narrower the sepal is. The next one, we can see much more convincing correlation between the petal width and the petal length. And it's a very strong 96% correlation right here. So the wider or the longer the petal, the wider or the longer the petal, right? So these grow linearly, as we would say, and the others don't. Now, a typical standard reminder here is that correlation does not equal causation. So we can, for example, imagine that the petal width doesn't cause petal length, but it's rather the growth of the flower. And sure, it might suggest that there is a causal relationship, but if we actually want to test if that is the case, we should run an experimental study and not just a correlation analysis. And we have to be very careful with these things that we don't analyze spurious correlations, as they are called, which is accidental ones that just surface by fitting 2 pieces of data together. There are some very nice examples of this. One is this particular one right here, which is on 2 different axes trying to plot the amount of people that drowned by falling into a pool versus the amount of films that Nicolas Cage appeared in. And as you can see from this, we would, you know, if we completely naively interpreted this plot, we might say that either the more people drown, the more Nicolas Cage feels committed to starring in movies, or that Nicolas Cage starring in movies causes people to drown themselves in a pool. And of course, the amount of features that we investigate now are only 2. There might also be a third one, which could be a confounder, which implies that it causes these to correlate. But there's actually a third one causing the strong correlation. So one kind of known example of this misassociation is that alcohol drinking and smoking correlate very heavily between them. So both alcohol causes smoking and vice versa. And we know that smoking causes lung cancer. And by that, you could also mistakenly infer that alcohol drinking causes lung cancer if you don't investigate smoking, right? So these are good things to keep in mind. I also note that correlation only captures linear relationships. And this is where the limitations of this metric come in. If you have data and you see a pattern like this, I really do hope that you think that there's something going on here. There is a pattern, right? It's this wavelength. So somehow something is causing some sort of oscillation in the data. But the correlation coefficient doesn't capture this, right? It only captures the covariance along this angle. And therefore, it will give a correlation score of 0 for this one. Same with these. These are all kind of interesting patterns. Here we even have some groups that we would really want to investigate. Now, one of the ways to use this kind of intuition of correlation in a prediction mechanism is regression. And as you remember, hopefully, regression is the prediction of a numerical target. It could be a range between whatever number. To say that we want to predict stock value, for example, it could be between whatever 0 and millions of dollars. So given some features, we would want to predict what the next value is, so the next step. Now the core question is, can we sort of model this correlation as a function? So can we fit it somehow so that the stronger our features are correlated, the better kind of prediction we make about what a possible new value might have as a target? And this is exactly captured in linear regression. And it's called linear regression because we are fitting a linear line. So just a single line along the axes. And the way that we do that is we have this nice formula over here. So either we have a model that receives some input, and that is defined as, where there should be an arrow, a times x plus b, where a is some weight and b is the bias. Or rather, our predictions y hat can be found using some intercept value and a coefficient. Right, so we have an intercept right here and a coefficient right there, and then we have our input feature. So notice that this is actually for a single one, so it should be small x, abiding by the notation that we've used so far. Okay, so what are these? So the intercept is the distance from the origin. So it controls the height of this line right here. So a very high intercept would start the line right here. And then the coefficient, or the weight, is the slope of the line. So if that is a negative slope, it goes from here to there. Here we have an almost 0 probably intercept, and then a positive coefficient, so it goes up right there. Okay. Now somehow we have to find this line, because this, given that this is a function, it's some continuous mechanism for generating these values. So whatever kind of sepal length we input into this function, so say given a 3, you can trace it right here, and then our sepal width would be somewhere below a 1. That would be the prediction right here, right? So how do we find this line? I worked out an example here, which I'm very quickly going to go through. You can pause and kind of go through it for yourself. The important part is that we measure the weight with almost exactly the same formula for the correlation coefficient, but then we only normalize for the data right here. Other than that, it's essentially the same. So we have the mean right here for our data. Now note that I kind of rounded this right here, so it's not exactly 18. There's the mean for our target right there. So this is just the sum over all our data points, and then divided by the number of data points, right? That's the mean right there. Another important thing to notice is that the shorthands for this part right here and that part right here are respectively here and here. So you can, rather than doing this summation, you can also take the full sum. So how to calculate these for each of the instances. So every row right here, that's explained here. That part is there. So if you sum these, right, you get this almost 1.66. Then when we have the coefficient, we can calculate the intercept, which is again the mean of the target minus the coefficient value times the mean of the data. And then finally we get our model right here. So this will be f of x. And if you input random values, or you can input the values that we fitted the function on, you will see that they kind of approximate the targets. Now this example, very quickly, has a few cities that are student cities within the Netherlands, and the data is the per 1,000, so this should be K, 26K students, and then the alcohol consumption over the norm of the Dutch Health Organization, right? So this is a percentage actually. Now just kind of squinting, you can already see that there is some relation right here, right? The higher the amount of students, the more the alcohol consumption, at least according to these three instances right here, we would say that students cause the alcohol consumption to go up, right? So you can go through this yourself, try to get familiar with how to do these calculations. And, you know, try some yourself on a smaller data set. Is actually a fun exercise. Okay, so here we have our initial points. Now I want to stress that this is fitted on the same data as we do the kind of prediction line on, right? So there's no real test data here. You could, for example, get a new city, get the data from the RIVM, look up the student numbers, and then put it in our model and see if that actually produces a good estimate. So I'll leave that up to you to do that. Essentially what we would say is that the data that this model is fitted on is our training data. So we train our model or fit it on this particular data set, and then whenever we have a new value, that would be something like a test set. We'll go into a bit more detail about this our next lecture. But usually we would want to have some percentage of our total data set aside to see if our model is actually good. Then we would input that right here. So the amount of students we would input into our formula, and it would give us some estimate along these lines. Now it could be that the model predicts, let's say, for 15,000 students that it's around 24%, right? Again, that's how we read it. This is our y hat. But in reality, it could be that there's a very high alcohol consumption. So our actual y would be right here, which means that we would want to have a sort of gauge on how much this error is so that we know if our model makes a lot of mistakes and how strong those mistakes are. So this right here is what we would call the residual or residual error. And we can see that even though we fitted on the same data that we test on at the moment, we already have a bit of an error here and a bit here. Okay, so this model is not perfect, and that is due to the fact that it's only a linear line that we fit, right? Ideally, we would want to fit a line that goes like this, right? However, fitting such a line that is exactly over these 3 data points might actually increase the amount of errors that we have because it's exactly fitted onto our data and it won't generalize. So say that we have new data, this very tight fit, which we call overfitting, which is that it exactly captures the data that we have, will probably undershoot a lot of the values that are here and overshoot a lot of the values that are here, only because we fitted it onto these 3 data points. Now, partly we can overcome overfitting by just collecting more data so that we have less of a tight fit, but there is always parameters that will cause a model to overfit, and this is something that we'll also go into in the next lecture. Now, just to show you the evaluation, again, normally we would have a test set on which we would want to run this, and we don't run our evaluations on the training set, other than maybe seeing if the model fit is good. But it won't tell us much about the predictive power on new data. It will only tell us something about the prediction power on the existing data. And if we do data mining, we're interested in predicting the values of new data, right? New data comes in. We want to use our models to predict this because those pieces of data don't have labels. If they had labels, then we wouldn't need this whole prediction module, right? So new data, no labels. And therefore, we would want to have some accurate measure of the error that we can expect, expected error, which is not generally aligned with the actual error. We can only see that once we have newly collected data and our model is kind of predicting in the wild. All right, anyway, just to go through this, kind of one of the standard ways of evaluating regression is doing root mean squared error. For this, we need our predictions, y hat and y. And again, we have this iteration right here. So we go over all the values in pairs between our y hat and our y. So again, say that this is these are the predictions, and this is the actual true values that, obviously the model doesn't know. Then the first y hat minus y squared would be for this value, and the next one would be for this, and then we sum that, right? So if we go back to our initial data, then we can find these particular values for y hat and y, right? So these are the predictions that we have. If you input the values of the existing data into our data set, you will get these 3 values. So these are our y hat. And the actual values were these, right? Those we know. And we calculate this. And if you're paying attention, you can see that I made a mistake right here because I didn't divide these by n. I didn't divide these by 3. So this value is actually 1.89. And then I'll leave you to figure out what the number here should be. We can get the r squared coefficient of determination right here, which is essentially how well our model predicts the targets relative to the mean, which is here. And it's equivalent to, in some regard, to the explained variance. Now, the way that we calculate mean squared error rather than root mean squared error, as you can maybe already tell, is just dropping the root. And the way that we calculate the mean squared error for the mean is that we go back to the values of the cities, and then we sum them, divide them by 3, you'll get the mean, and then you input the mean into these numbers right here, and then you will get mean squared error for the mean. We also want to redo that for that, so dropping the root, which means you can also just square this if you want. So in some sense, that would give us an indication of how well the model fits the data. Okay, so we've seen how we do prediction for numerical targets. But what happens if we want to do classification? So if you want to essentially label particular parts of a data as being certain categories or classes. So thinking back to what I said before, whereas with regression, our target was numerical, now it's categorical, and we have to separate our instances rather than fit a line that explains them, right? That is the essential difference between regression and classification. Now, luckily, we can plug in what we already had, which was fitting a particular line across our data to separate them. So you can imagine that fitting a line to separate our instances would be kind of the same as trying to fit along them. Just there's a different objective, namely, do we successfully divide our instance space with what is called a decision boundary. Now, I'm not going to go into a detailed explanation. That's maybe something that would be good for a machine learning course, but I just wanted to show you the formulas and give you two intuitions about the formulas. One is that we indeed plug in exactly our regression model right here. That is how we get the probability for a particular class. And then there's a second one, which is to that probability, we apply a logit function, which is also sometimes called a sigmoid. Now, what that means is that this results in a particular probability, and with the logit function, we can squeeze that probability, which is between 0 and 1, to any of these as our labels, right? So it's either 0 or 1. So whatever is between there is squished to either 0 or 1, which is how we get our prediction targets. So I'll try to also give an intuition how this line fitting sort of works, and how the sigmoid comes into the linear regression that we used before. Okay, so previously we had our data, right? And there was a bunch of points. And we had this line that we made sure was nicely snuck in between these points here. And then we got some particular error if we tested our model. Now, these values didn't really have a, we checked it for 2 dimensions. Obviously, if there's a third dimension, then the linear line that we drew is more of a plane, so it goes into 3 dimensions. See, so it's more like of this 3D line. Now, this kind of similar intuition is applied to logistic regression, where we have our data, and now our kind of third dimension is the label. So we know that we have our class 1 and our class 2, and we want to, rather than have this linear line that sort of tries to explain how our features and our label relate, we now have 2 feature values, and we want to somehow fit a line that divides this space so that one side is a particular y and the other side is another one. So how do we do this? You can imagine that we have a line, and if you would hand draw it, so let's say we draw it right here, there's 2 sides of the decision boundary. There's the left side, which is 0, and then there's the right side, which is 1. And this particular thing is done by the sigmoid function, because the sigmoid function is actually a third sort of dimension onto this decision boundary right here that pushes everything on one particular side to a 0 and the other to a 1. So the sigmoid looks like this, and we can fit how fast this line kind of goes up. So how tight this is. But this is essentially in 3D, you can imagine that this wave is over here. So it goes, for example, up this particular point and down that particular point. And therefore it knows that everything underneath the sigmoid should be a 0, for example, and everything above it should be a 1, or the other way around. Okay? So just to quickly, I mean, it's difficult to draw this in 3D. But imagine that rather than this plane right here, we have like a sigmoid like this. So this is our box, right? And then we have some features here that are above the sigmoid. And we have some features here that are below the sigmoid. Okay. So these would be, according to the sigmoid, 0 or 1, and these would be 0. Okay, that's the intuition. That's all you have to know. So the success of this decision boundary is determined by how well we fit and sort of classify. So in this particular example, if we classify everything on this side as 0, we have 10 instances, and all these are 0. We have 2 of our one class correct, and then the others of the other class correct. So there's 3 instances that we didn't predict correctly out of 10 instances, right? So that is 70% accuracy for this particular line. All right, so this is the percentage of correctly predicted instances given a binary target. Now you can imagine that we start moving this line to here, right? Somehow. That position gives us 1 incorrectly predicted target. So that gives us a 90% accuracy. And we move it up again, right there, and that will give us 100% accuracy. So everything on this side would be 0, or, you know, let's call this 0. This is 1. This would be 0. This would be 1. And therefore, we predicted everything correctly. Right? So everything here is on top of the sigmoid or below, and the other way around. So now the question remains, how do we, you know, this is our line that we had before with linear regression. It's the same type of line, which also has an intercept and coefficients to determine the slope. So it's the same deal, but somehow we have to tune both the intercept and the coefficients to get this nice, snugly fitting line. So you can imagine that there's a range of possibilities. So a range of numbers for both our intercept and our coefficients, right? And we can imagine that for each combination of a particular value of the intercept and a particular value of the coefficients, that there's an associated accuracy, right? So we move this and then the accuracy differs. So you kind of get this point, you know, if this would be kind of like, these are the values right here. This is kind of a matrix. These are the values right there. And then these are all possible different, you know, this is very long, but just imagine that this is the case. We have some position that has our 90%. There's one that has our 100%. There's one that has 70 right here. Now this might be 80, 80, 90, 60, 60, etc. Somehow we have to navigate through these particular points the correct kind of combination, right? So if we start here, we can calculate using derivations. So we're not going to go into this, but we can calculate somehow that this is the correct way of going. This gives us a higher accuracy, etc. And then we stop until we have sort of the highest possible fit, and then all the kind of parts around this don't give us any improvement. Now you can this is, if you know that this is continuous and this is continuous, this is a gradient. So it's like this smooth line that gives us particular performances. And the way that we can fit logistic regression in this kind of way is called gradient descent. You can imagine this is, a position right here. This is a position right here. Somehow we have to find along these slopes the optimum. So this is called hill climbing. And this is part of machine learning, so I'm not going to go into much more detail than just the intuition. But we want to find the optimal fit, which is the optimal combination of coefficients and intercepts right here, which will give us 100% accuracy. So this was the intuition about logistic regression and how we make these decision boundaries. For now, you just have to remember that we have this accuracy. We can optimize for different things. Gradient descent actually optimizes for different things, but the way that we evaluate this is accuracy. So just explain it like this. And in the next lecture, we will go into a bit more detail about these evaluation metrics for classification. Now, another way of drawing these decision boundaries can be, rather than fitting these lines, we can look at the instances. So the labels that we know of the instances, and then a way to memorize all of these and kind of infer new labels is KNearest Neighbors. Now we'll go into a more detailed explanation regarding KNearest Neighbors in the next lecture, but I just wanted to visualize it for the iris set because it actually works very nicely. So if we would have logistic regression here, we have 3 classes, so we need 2 decision boundaries, right? We need one that separates our setosas from our versicolors right here, and then we need one that separates our virginicas from the versicolors. Now, as you can see, we already have some errors with the lines that I drew. So is there a way that we can do this more nicely just using memory? Because logistic regression just fits a line and doesn't remember anything. There's nothing in memory. It just fits these lines and it remembers those lines. Now KNN remembers all the points. It knows the whole training set is in memory. All these locations right here are stored. And then if we have a new instance, for example, right here, and we can say, okay, let's look at the nearest neighbors, K. Let's say we say K is 3. We can see that, for example, this could be a nearest neighbor. This could be the second nearest neighbor. And then we have this one as the third nearest neighbor. 2 of these neighbors are versicolors and one is a virginica. So most probably this particular instance would be a versicolor. So again, this is good to remember. KNearest Neighbors works by memorizing everything, looking at the closest instances, and then doing the classification based on this. Now, if we were to apply this to a test set, you can see that right here, it will classify all of the test set correctly based on the neighbors. And the kind of decision boundaries, at least for 2 classes that it makes, look like this. So you can see here that there's some probabilities of particular classes based on their positions. So the further away it's from the core of the fitted instances, the less likely it is part of the class. Now, if you go back to here, you can see that this is the decision boundary for a versicolor, which were all clustered around here, right? So if it's within this range, it's very likely a versicolor. I will go into a bit more detail on some of these distances in the next lecture, but I wanted to give you some of these to work out for yourself. So some ways of doing distances are, for example, the Manhattan distance, which calculates distance as it were kind of like a road. And similarly, if there was an instance right here, it would, for example, take the shortest route. It would take the route right there. It would kind of snake, as it were, like this to the instance, and then give some sense of distance right there. So this is useful when the features are, for example, categorical. Then there's Euclidean distance, which calculates the distance between 2 points. as we know this length and this length. So through the Pythagorean theorem, we can calculate the distance right here. And we have the Minkowski distance, which captures both of these in one particular formula. We, for example, also have the Hamming distance, which for strings, for example, calculates some added distance between two of them. So you can see here that these bits are flipped right here. There's two flipped bits, so the distance between this particular string right here and this is 2. So these are different metrics that we can use within KNN to do distance based on the features that we get and their values. More on KNN in the next lecture, and also look at decision trees. A lecture after that, we will go into more detail about evaluation. So see you in those videos.